Hi, I'm Cesar. It is our second part about the computational fluid dynamics series. I hope you watched the previous video which discussed about the basic of finite difference method, and I explained about the difference or maybe the like several equations from the finite difference method for the first order and second order partial differential equation. And in the second part, I want to use those equations, maybe one or two of those equations, as a case study, with the case study as the transient simulation of the heat conduction, but I will just use it like the 3D, like a one-dimensional problem. So I will make it or keep it simple so you can follow this series easily. Okay, let's just jump into it. So the transient heat equations governed by the Fourier's law, and actually it's like a three-dimensional heat equation, but I reduce it to only one-dimensional, so we only use the x direction here, and we keep this delta t here for the time or the transient term. So this equation, or the second order partial differential equation, also known as the the diffusion equation. So maybe I will discuss it later. By I hope if you understand this, it will be easier to explain about what's the difference between the diffusion equation, convection, and anything like that. So to make the equation simple, I wrap this rho, Cp, and K into the alpha, or the alpha is the thermal diffusivity. And we will try to solve a very simple problem here, like the 1 meter metal rod, and I will set the temperature for the rightmost part of the rod to be 100 degrees Celsius, and the leftmost will be 100 and the rightmost will be 30 degrees Celsius, and I will simulate it like 60 seconds. I just guessing some number here with the physical data which I get like randomly from the internet, just to let's just try this random number. We don't want really want to get some exact value. I just want to focus on the numerical method. So I just calculate the alpha here, and so we can expand this equation to the discrete form like this. So for the time term here, you see this, the time is the first order and the space is the second order, so the time will be in this form. In the central difference, we discussed this form in the first part, and then for the second order I will expand it like this. So it should be plus the truncation error, but we will just ignore it. And this scheme, also known as the forward time central space, because the time will be forward, like from n plus 1, and the central space means that the space consists of the I plus 1 and I minus 1. It means that we use the space left and right, but for the second order we also have this center term here, dti, and if we see here, we get the n, 3 n's, and only 1 n plus 1. So it means we can break down it like this. The ti n plus 1 is equal to everything in the right hand will be n. So we will compute it like the t over time. So we will like calculate it for n, then n plus 1, n plus 2, and so on and so forth. And we also define new parameter here, s, which is equal to the a times delta t divided by delta x squared, just to simplify these constants. So we assume that the delta t and the delta x here are constant. Actually, in the real CFD solver, if you make a mesh or like adaptive time control, it will be not constant, the delta x and delta t. But for this simple problem, we will assume that the delta x and delta t are constant everywhere. Okay, so the equation will be in this form, and okay, it is quite simple equation actually. We just need to define the in, the I minus 1, t plus 1, and so on and so forth to get the tn plus 1. So the next step is to define our computational domain. So as this equation suggests, the steps will be calculate this first, the I, or like everywhere in the x direction in this specific time, then we go to along the time. So we just use this direction n and this direction x. So it is not actually like two-dimensional because the y direction is the time. Like the vertical direction is the time. I hope you get the idea. So we can make it in this form. For example, we will solve this by using Excel. Actually, because it is just like a very simple. You can do it by yourself. And I will divide the x direction into 10 or 11 because we have also 0 here. 0 to 10 is like 11 points or 11 nodes. So the delta x will be 1 meter divided by 10. Oh, sorry, I mean 10 because it is like not really much. And also for the vertical direction or the time direction, it will be 20 nodes also. So the delta t will be 3 seconds. So from here we can calculate the s value. Okay, and so our goal is to fill this whole like this whole table here by the value of the ti, n. Okay, so to fill this table, we use our TF, wait, I forget it. FTCS, or forward time central space, or this equation we already defined to calculate its block or its mesh. So for example, if we want to calculate this blue box here, the I, n plus 1, we just refer from the previous value here, the in, ti minus 1, n, ti n, and ti plus 1, n. So we can fill this equation to get this ti n plus 1. So in the vertical direction, the n will be growth, and in the horizontal direction, the value of I will be moving. So I hope you get the idea. It is actually just very simple. And to get the value here, for example, if we want to use this equation, we should have the ti n and ti minus 1 n and ti plus 1 n. So if we just use these unknown values, we actually cannot fill the equation and cannot find the solution. So the first step we must do is to set some boundaries values here. For example, in the left side we will input the 100 for I equal to 0 in every n. Sorry, yeah. For every I equal to 0 for every n. And from the rightmost part, we will just input 30 everywhere in the I equal to 10 and n equal to like everywhere in the n value. I hope you don't get confused with this. And it will be logs the number, and also for the lowermost part I will input 30 here as the initial condition. So we assume that this rod is initially has 30 degrees Celsius when the time equal to 0 or n equal to 0. Okay, by input this we can actually calculate this box here, this unknown box. We can input the equation here to get the value of or to complete or to fulfill this equation to get this field. Or maybe you can also calculate here, or actually you can also calculate it simultaneously. We will discuss it later. But in this sample, I will use known as the explicit method. So we input it one by one here. From here, after we get this value, we calculate this one, the right part. Then after we get this, we calculate this, and so on and so forth. After all this, after this complete, we just moving up to calculate this, because we already have these 3 values underneath this mesh or nodes. And we go to the right direction again, and go up and the right direction, and so on and so on and so forth, until you get the everywhere here filled with those values. And it's called explicit method because we just used from the previous value and previous previous result to get the new result, or n+1. So this is the code, or the form of the code if you are using MATLAB, but I will not discuss the detail here. Maybe we'll make a special video especially for this, but the idea is just the same. We make the initial value here for the I, 1. It means that the value of time is 1 here, so I use the 1 as the first value here. It's just the same as defining this. And for t1, n+1 means that for the t1 means that I is equal to 1, means that this nodes here, the leftmost part, will be 100 for n+1 for n up to the last n. Also for this one is n+1, n+1 here means that the rightmost part will be 30 degree. And for the other parts, like the unknown parts, we will define as the governing equations, which we discussed previously. Here it is actually just the same with this, so you can write it down like this. With MATLAB it is actually very simple, and the result will be like this. So you can get the whole mesh or the whole table filled with these values. So you can expect that the lower value of delta t, or maybe the the more number of the mesh will make the value or the curve will be smoother. If you can see here, it is not as smooth as we expect. And also for the delta time, if you make it smaller, maybe the value will be smaller. But we will just discuss later about it. So I hope you get the idea of solving this whole table. So actually, just like the idea of the numerical method is just like this. And the other method to get this whole value, this whole table, is using the implicit method. So the implicit method is using the n plus 1 in the left and the right side of the equation. So if we input it one by one like this, it will not complete, because if we want, for example, if we want to calculate the value here in the blue box, you need the value from the left and the right, but unfortunately this right side is unknown, so the value will be unknown. And in the right side we get also the ti n plus 1, which is the same as the left side, so this block will be in the two sides of the equation, and obviously it cannot be solved explicitly. So the way to find this value or the solution is to make it in the form of matrix like this. For example, if we get the previous matrix as the table, we can change it to this form, and we will discuss the detail about how to solve this, because it will involve a lot of techniques like the Crank-Nicholson maybe, or maybe the McCormack method, and many more. We will discuss it later. But for the implicit method, it will be faster to get the whole domain compared to like the explicit method one by one. But for for the implicit, you need a huge matrix to solve. Of course, you cannot do it like manually, or maybe in the CFD we will need like the more memory to store this matrix. So it will be very important in practical point of view, but we will discuss it later. And maybe that's all for this video. In the next part we will discuss about the stability of our scheme. So stay tuned in this channel. Thank you for watching. I hope you subscribe if you like this video, and leave me a comment in the comment section below if you have any question, or maybe some requests to the other to the next part, or maybe the other video if you want to discuss. Thank you for watching.